In the field of science, the huge mysteries pertaining to what was prior to the enormous explosion have sparked mixed conversations and fascinated thinkers for quite a while. This vast question doesn't just test how we could decipher the universe, it challenges the genuine furthest limits of human knowledge. Imagine standing at the edge of existence, examining the colossal shadows, and pondering what lay there, what existed before our universe was even imagined. The event of the Big Bang marked the beginning of all things, including time and space. Yet, was there a second earlier? In the past, there might have been a condition of nothingness, a calm before the cosmic gathering began. And if this is true, was it truly nothing? Or perhaps, was there something much more alarming that existed before the beginning of time? As we dive deeper into this question, science takes us on a journey beyond the universe's beginning point, into thoughts that challenge our very consciousness. Physicist Brian Cox, well known for his examination of the wonders of the universe, suggests that surprises may have existed prior to the massive explosion. He urges us to reconsider our perception of the world and existence. In this investigation, we will dissect theories, examine research, and uncover dazzling insider information that could help us understand what happened before everything else. We'll explore concepts like self-important development, quantum alterations, dark energy, and multiverse as well. The responses we uncover may just paralyze you, yet they could also open new understandings of our place in the cosmos. Prepare to plunge into the depths of the universe, into a realm that defies imagination and science, where the unknown still wins around the shadows, leaving scientists shocked, and sometimes even unsettled. We ought to explore what existed before the Big Bang and why these theories test everything we thought we knew. To appreciate what may have existed before the Big Bang, we first need to meticulously examine what the Big Bang was. So, what was the Big Bang, according to scientists? It was the point in time when the universe became extremely hot and dense, rapidly expanding to cause the growth of all matter, energy, and existence. When we look at the night sky, we see no boundaries. It reveals evidence of this hot beginning, galaxies spreading out in every direction from an early stage. But why did this happen? Furthermore, was there a period before this thick, hot start? According to the idea of massive expansion, there was indeed a before. However, it lacked any semblance of void or peace. The vast expansion suggests that before the Big Bang, the universe was in a state that was cold, vacant, and loose, basically resembling a huge vacuum. Nonetheless, this vacuum was not entirely empty. It contained a gigantic amount of energy that fueled the rapid expansion of space itself. This expansion, called inflation, happened so quickly that it essentially established the groundwork for everything that followed. It was part of a later phase where space expanded at unimaginable rates, before the inflation slowed and the energy transformed into particles of matter and the forces we now observe. But what was the nature of this energy? Why did it suddenly grow the universe? And why did it stop? Specialists believe this cosmic inflation created patches of the universe, each experiencing its own expansion. Imagine a fabric expanding after the Big Bang, endlessly, with minuscule air pockets forming here and there. Each air pocket represents a universe, including our own. This concept, called the inflationary multiverse, suggests that there are conceivably endless Big Bangs and an infinite number of universes. Ours is just one of many. This huge, mind-bending reality challenges our understanding of the very universe itself and leaves us with the question, what else is out there? The idea that there was nothing before the Big Bang is speculative at best. According to our current understanding, even if you eliminate all radiation and particles from the universe, it would still not be genuinely empty. Our universe is filled with dark matter, dark energy, quantum fields, and other forces that weave an inevitable tapestry of something, even in its most vacant form. Even if we imagine stripping away all of these forces, leaving a dead space, the universe would still generate new kinds of energy. This reality alone is bewildering to experts, as it suggests that true nothingness might be impossible in our infinite universe. Understanding space itself, its properties, rules, and constants, prevents it from being completely empty. Imagine trying to create a region with literally nothing in it, no particles, no radiation, except quantum fields and fundamental constants. These would continue to exist, implying that even non-existence has properties. For example, a phenomenon known as zero-point energy represents the least amount of energy possible, the ground state of quantum fields. In this state, particles can still momentarily appear and vanish, creating an unsettling reverberation of motion in what should be empty space. This challenges our idea of a true void and suggests that, yes, even before the Big Bang, something may have existed that scientists are only beginning to understand. One of the most astounding theories in current cosmology is the possibility of timeless expansion. If inflation caused our universe to exist, it's possible it could continue forever. Brian Cox describes an astonishingly high inflation multiverse, where universes are infinitely created and continue expanding. Imagine each Big Bang as another universe being illuminated by a flash, while inflation continues in other areas, creating numerous other universes. This cycle could, in theory, go on for eternity. This concept leads to the wonderful idea of a fractal universe, where each new universe might produce its own Big Bang. Each universe exists as a separate, independent domain, unaffected by the others, as a result of the rapid growth of space. This hypothesis is both exciting and unsettling for researchers, as it suggests a never-ending multiverse with no definitive beginning or end. Imagine our universe being just one piece in a gigantic cosmic structure that never stops growing, constantly making new universes. And what if the upsetting truth is that there is no before or after at all, but rather a timeless universal pattern, one that's constantly developing and decaying? Our understanding of nothingness changes when we consider quantum field theory. According to this, the universe is more than just a collection of matter floating in space. Rather, it's a complex network of energy fields that fill the cosmos, connecting to create everything we see. These fields are like invisible oceans, with waves or particles acting as ripples. Even at their lowest energy state, the vacuum state, particles can still appear and vanish, momentarily borrowing energy before returning it. This phenomenon results in virtual particles, substances that briefly exist and then vanish, leaving only faint traces. The idea of virtual particles challenges our concept of a real void. Imagine an empty universe, where all radiation and energy have been removed. Would that be nothing at all? According to quantum field theory, it wouldn't. Even in a vacuum, fields remain active, sometimes generating transient particles. This persistent activity in what should be nothing suggests that the universe does not recognize our concept of emptiness. If scientists were to detect primordial gravitational waves, they could potentially offer the first observable evidence of what occurred before the Big Bang. These waves, rippling through spacetime since the very origin, may carry information imprinted by the inflationary process or by events even earlier, events that existed in the pre-Big Bang landscape. Experiments like LIGO and future missions like LISA and the Cosmic Explorer are being developed specifically to detect such faint, ancient signals. If successful, they could reshape our understanding of cosmic history and possibly prove the existence of other universes or previous cycles in a never-ending chain. But as we look further backward, we collide with a wall, a conceptual barrier, because time itself is believed to have been born with the Big Bang. According to Einstein's theory of general relativity, space and time are interwoven, and without space, there is no time. So to ask what happened before time is, in a sense, asking a question that breaks our current physical laws. However, modern quantum theory suggests that time may be emergent, not fundamental, but rather a byproduct of deeper quantum processes. If this is true, then before the Big Bang could have been governed by entirely different rules, perhaps governed by a timeless quantum state where the universe existed in potential, waiting to be realized. Some theories, like loop quantum cosmology, propose that the universe didn't begin with a singularity at all, but instead bounced, collapsing from a previous universe and then rebounding into expansion. This big bounce theory removes the notion of an absolute beginning, proposing instead a cyclic process with no starting point, just transitions. Others look to string theory and M-theory, which suggest that our universe is one brain in a higher dimensional space, possibly colliding with another brain to create what we experience as the Big Bang. In this framework, our universe might just be a three-dimensional surface floating in a higher, unseen cosmos. Brain collisions, like two sheets slamming together in a cosmic dance, could produce repeated Big Bangs, each the birth of a new universe. This leads us to an astonishing and humbling conclusion. We may never fully grasp what came before the Big Bang, not because it's impossible, but because the tools we use, our language, our physics, even our imagination, are tied to this universe's rules. But what if we embrace that mystery? What if the value isn't only in finding an answer, but in the endless pursuit of it? The search itself may unlock not only the secrets of the cosmos, but something deeper about who we are, curious beings reaching for meaning in the infinite dark. Prior to the Big Bang, should they be identified, they might provide proof of the universe's previous states. The potential discovery of early-stage gravitational waves is one of the most exciting possibilities in cosmology today, as it might not only expose the truth regarding the Big Bang but also offer a glimpse into the cosmic state before our universe was born. This theory presents an enticing prospect, detecting gravitational waves that could serve as evidence of a previous Big Bang universe. As we continue to investigate what might have been before the Big Bang, we explore ideas that push the boundaries of our understanding, challenging even our most fundamental presumptions regarding space, time, and existence itself. One of the most mind-boggling ideas comes from the realm of quantum gravity, a field that seeks to meld general relativity and quantum mechanics. This merger may or may not reveal a unified theory of everything and might offer insight into what existed before the Big Bang. According to quantum gravity, time and space are not smooth, continuous entities as we experience them, but instead are discrete, granular structures. According to this theory, the space-time fabric itself could have been formed from a structure on the microscopic Planck scale, with tiny quantum fluctuations shaping the universe in ways we cannot yet fully comprehend. What we perceive from this perspective as the smooth space-time continuum and time might have only emerged from these fluctuating quantum fields. Thus, the before the Big Bang could be described by a radically different concept of reality, one where space and time themselves were not fully formed. Another possibility is that the universe is part of a vast cosmic landscape filled with potential universes with distinct physical characteristics, laws, and constants. This theory, known as string theory, gives rise to the string landscape theory, which suggests that all fundamental particles are, in fact, extremely small vibrating strings. In this framework, there are many possible configurations of these strings, each corresponding to a different set of physical laws. The string landscape could imply that our universe is just one of many, each emerging from a distinct Big Bang-like event. The existence of such a landscape also brings forth the notion that other universes might have different strengths in different dimensions of gravity, or even various kinds of matter. In this view, our universe might not be unique, but rather a part of the multiverse, a collection of universes, each evolving independently. The multiverse theory provides a speculative yet fascinating answer to the question of the universe prior to the Big Bang, another universe, arranged in a different way, potentially leading to infinite cycles of creation and destruction with no definitive origin. In addition to these cosmological models, some theoretical physicists have also considered the role of black holes in shaping the universe. A hypothesis gaining attention is that our universe could be caused by a black hole formed in another universe. In this scenario, the singularity at the center of a black hole could serve as a gateway to another universe, with the Big Bang being the moment when such a black hole gave birth to our cosmos. This hypothesis is bolstered by the fact that, in accordance with general relativity, the singularity at the center of a black hole is a point where space and time curve infinitely, creating a region where the known laws of physics break down. It's possible that the extreme conditions inside black holes could lead to the creation of new universes, which may suggest that what we consider the Big Bang was just the birth from the singularity of an ancient black hole. Exploring these concepts requires a deep dive into the very nature of time itself. Some cosmologists speculate that time as we recognize it might not have meant anything before the Big Bang. If time began with the Big Bang, then there may have been no before in any conventional sense. According to this view, time itself might have emerged from a quantum fluctuation or from a primordial state where the usual distinctions between past, present, and future did not apply. This could lead us to reconsider the idea of causality, which relies on the assumption that events take place in a straight line. If time did not exist in the way we experience it, then the question of what came before the Big Bang becomes absurd, because there wouldn't be any temporal framework to support it. Further complicating the picture are theories of cyclic time. As mentioned previously, cyclic cosmology suggests that the universe goes through endless cycles of birth, evolution, and eventual collapse. In this model, the Big Bang could represent just the most recent bounce in an eternal series of universe cycles. These cycles might not be identical but could evolve in different directions, each with unique physical properties. The cycle of the universe, according to this theory, would be a continual process with no true beginning or end, rendering the question of before the Big Bang meaningless in the conventional sense. The idea that time itself might be cyclical suggests that every Big Bang could be followed by a contraction and another big crunch, with the universe reinitiating itself in an endless loop. Another avenue of investigation into the nature of the cosmos is the potential of a primordial soup of particles and fields that existed before the formation of galaxies and stars. This idea suggests that before the universe began its rapid development, it was filled with a dense and hot collection of elementary particles, comprising all quarks, leptons, and bosons, in a state of extreme energy. These particles would have been interacting at very high temperatures and densities, laying the groundwork for the formation of energy and matter. As the universe cooled, Some versions of this theory suggest that this primordial soup existed in a quantum foam, where particles kept appearing and vanishing due to the uncertainty principle of quantum mechanics. The soup's properties have the potential to offer insights into the universe's earliest moments, and, by extension, what ultimately preceded the Big Bang itself. The world before the Big Bang still exists as one of the most profound mysteries in science. As our understanding of quantum mechanics, cosmology, and fundamental physics deepens, new theories will continue to appear, providing increasingly complex and sometimes paradoxical explanations for the origins of our universe. While we may never fully grasp what came before the Big Bang, the pursuit of this knowledge will continue to stretch the limits of human curiosity, driving us to explore the unknown frontiers of existence. This ongoing quest to understand what came before the Big Bang also prompts profound philosophical and metaphysical questions. If time itself had a beginning, what does that imply about existence? Can there be a before, if the very fabric of time did not yet exist? These are not merely scientific inquiries, they touch on the essence of reality and our place within it. As we expand our observational capabilities with tools like the James Webb Space Telescope and next-generation gravitational wave detectors, we edge closer to collecting data that could validate or refute these mind-expanding theories. The echoes of ancient gravitational waves, the signatures of quantum fluctuations, or the structural anomalies in the cosmic microwave background may serve as the breadcrumbs leading us back to the universe's earliest, and perhaps pre-universal, conditions. The possibility that our universe is one of many within a multiversal ensemble forces us to reconsider the anthropic principle, the idea that the universe is the way it is because we are here to observe it. In a multiverse, life might emerge in countless forms under radically different conditions, suggesting that our universe's finely tuned laws are not unique or special, but one random outcome among an infinite sea of possibilities. Yet, even as theories grow more intricate and speculative, they remain grounded in our desire to comprehend the ultimate origin. Whether through the lens of string theory, loop quantum gravity, black hole cosmogenesis, or eternal inflation, scientists are, in essence, asking the same timeless question: why is there something rather than nothing? Perhaps the answers lie not just in equations or observations, but in a fundamental shift in how we perceive reality. Future discoveries might force us to accept that our intuitive notions of time, causality, and existence are inadequate, or even illusory. In the end, the mystery of what came before the Big Bang may never be completely resolved. But the journey toward understanding continues to inspire the deepest intellectual exploration humanity has ever undertaken. It's a pursuit that binds science and wonder, reason and imagination, reaching beyond the stars, into the very heart of creation itself.